Hello and welcome to the Innovating Coastal Resilience Summit. I'm Sharon Ryan, your moderator for today's workshop. Thank you all for joining us. We're now in week 4 of the Summit series, and I'd just like to take a moment to acknowledge the tremendous response and active participation of people from across industry, government agencies, nonprofits, and academia. As a result, we've had a number of rich, informative conversations and exchanges around technology and coastal water quality issues. We've talked about the needs of end users for real-time, accurate information on coastal water quality hazards and the kinds of channels and platforms that could communicate coastal sensing data more effectively to decision makers and the public. We've also spent time in our breakout groups thinking about how technological change will affect the future of the workforce, the different skills that the workers of tomorrow will need, and strategies for preparing the next generation of professionals for success. Last week, we looked at what's driving the development of new sensing technologies. And a common theme coming out of all the workshops is that although we've gotten really good at using sensing technology to collect reams of data on coastal water quality, too little of this data sees the light of day. And where it does, it's often not delivered in a time frame or manner that best supports proactive decision making. So today our conversation is going to explore some of the ways that we can leverage artificial intelligence, data science, and data engineering to get better and faster at accessing, integrating, analyzing, and making sense of data for the various end users who need it for decision making. So that's from public health and natural resource managers to fishers and tourism operators, for example. And we're also going to brainstorm a little bit on the future workforce development needs specific to AI, data analytics, and data engineering. So we just did a little quick poll there to get the conversation going. So we asked everybody, is AI a force for good or evil, or is it just complicated? So I'm going to end that poll and share the results with you right now. So from the replies that we got, let's see, 39% think that AI is a force for good, so that's good, I guess. No one thinks it's a force for evil, and 61%, so that's most of us, I guess, think that it's complicated. So that makes sense to me as well. Right now, I'm just going to walk you through our agenda. So just give me a sec, and I'll get this up on the screen for you. Okay, so following the introduction, we're going to go into 3 talks today, and those talks will last for about 45 minutes. And during the talks, we want to invite you to type any comments or reactions or questions you have for the speakers right in the chat. Our first presenter today will be Alex Beavers. He's with the Mote Marine Laboratory, and he's going to be talking about the use of artificial intelligence in data analysis for coastal waters. Next up, we'll have Rick Stump from the NOAA National Centers for Coastal Ocean Sciences, and he's going to review for us the state-of-the-art tools in remote sensing of hazardous algae blooms. Farron Wallace of the NOAA Southeast Fisheries Science Centers will then explore some of the challenges of AI and analytics in a marine environment. So we're looking forward to those talks, and welcome to all of our speakers. Thanks for joining us. So following the talks, we're going to pose some of your questions in the chat to the speakers. And if you'd like to ask a question out loud, just raise your hand via the participants button, and I'll call on some of you to ask your questions. So after that, we're going to move into breakout sessions for about 20 minutes or so, where we'll invite you to share your insights and expertise on the topic at hand. And at 2:15, we'll bring everyone back to the plenary group and invite several of the conveners to share the highlights from their group's discussions with the plenary out loud. And also in the chat, you're welcome to share your thoughts in the chat as well. Before closing up today, we'll share a link to a survey where you can expand on your comments or add new comments. And we'll be sharing that link throughout the day. So please, when you see it go by, grab a copy of it and go to it later and complete it. We'd really appreciate it. So we'll wrap up this afternoon's session with a few words from Christine Angelini on next steps. And some of our speakers and organizers will also be staying around after the sessions, and they'll be happy to answer any additional questions and chat further with participants. So at this moment, I'd like to invite Alex to share his presentation, please, and begin.
All right, thank you very much. Appreciate it. And let's see. So first I'd like to introduce Mote Marine Laboratory. This was a nonprofit research organization that was founded more than 60 years ago. We have 6 campuses across Florida, although our headquarters is in Sarasota, Florida. We have several hundred researchers that are supported by more than 1,000 volunteers in all the activities that we do. We've been conducting research and creating innovation in 3 major areas over these 60 years. First of all, in the ecology, chemistry, and biology related marine sustainability areas. Secondly, in marine-derived biosciences based on research into marine animal genetics and microbiology. And thirdly, in an area related to the industries that support the blue economy, our water-based industries such as aquaculture, aquaponics, and so forth. At Mote, we've been building something we call the Mote Learning Engine, which is the application of machine learning algorithms to help improve the sustainability and productivity of some of these industry-related activities, marine science-related activities. Now let's talk about the 3 technologies that are a topic today and the fact that they are tending to converge. Artificial intelligence, of course, is a blanket that we've thrown over a lot of different things over the last 10 or 15 years, although that term itself was originally used in the 1950s. But basically, today it relates to the automating of learning from and the use and automation of the use of data. Data science has been emerging over the last decade or so. We often hear that associated with data analytics, basically helping drive the making of decisions that are based on a lot of data analysis. And as we continue to digitize our living environments with Internet of Things and lots of digital sensors that are showing up in our consumer and industrial products, data engineering has become another important topic for us. When we look at how these technologies are overlapping, there's several key things that are important to each. Of course, data sets, and the preparation of data is critical. As I said, we're generating more and more and massive amounts of data. Another key aspect of this are the algorithms that we're developing that are part of machine learning that help us learn from the data and inform our other research and decision areas. And then as we have more and more massive amounts of data and more of it's streaming or live raw data streams, we need more data engineering application, or more data engineering expertise to make sure we have scalable data structures because our classical database management techniques just are not up to the challenge. When we look at the skill set overlaps, we see that systems integration, of course, is a key to a lot of this. At the body and the heart and soul of all of our machine learning algorithms, of course, and our data analytic techniques are things that a lot of us didn't want to think about in our education as statistics. The role of statistics in our modern technologies is becoming more and more important, and we'll talk a little bit more about that in a few minutes. As we're able to process larger amounts of data and generate more knowledge and more associations and identify more causal relationships, we need to make the data not only available for machine use, but also for human use. So the whole concept of data visualization is becoming more important. How can we as humans look at massive amounts of data and understand its temporal and geographic relationships? As we think about overlaps and applications, I mentioned that data science recently has been making a lot of impact on business and management science. All of us today in our daily lives are the things that we do our digital footprints being evaluated digitally and helping create a lot of decisions that by the businesses that we interact with and the services that we receive. The engineering sciences, of course, have been dependent on data analysis forever, since day one. But it's just recently that we've seen opportunities and had the ability to start thinking about how do we apply artificial intelligence to the natural sciences and especially marine sciences. So there's a lot of opportunity there that where we can actually build on what's been happening in management science and engineering science. So let's talk a little bit about the tools available in this whole space. When we look at first of all, we tend to think in terms of languages, algorithms and platforms, and of course, who's providing those for us or to us. If you look at different surveys on the most popular programming languages, Python tends to pop to the top of the list. R and Java or other languages are very popular. And then there's another 10 or 20 different languages that have been used by various people to help program applications in the artificial intelligence and data science spaces. Another thing that's happened over the last 10 years is quite a few high-tech companies have commercialized their algorithms and platforms. Google, for example, has TensorFlow, Facebook has PyTorch, Microsoft has quite a few tools in their Azure cloud, and there's quite a few other companies that are in the business of providing either for free or for a fee algorithms and platforms for applying artificial intelligence and data science applications. So let's get back to the core question: is why would we want to use AI for marine science? First of all, as I said, there's as we've heard in the last 3 webinars, and we continue to talk about it, and the other speakers today will be talking about this. We're generating a huge amount of data that up to now has required a lot of human processing, a lot of manual activities. So that we hope the benefit from the use of AI technology will be to help us automate our analysis, discover new and more causal relationships and create more information, and to do this discovery faster. So our generation and collection of data is outrunning our ability to handle it and process it effectively. So we do need these tools to help improve our productivity there. A couple of comments about what machine learning is all about. Most of our applications that we are very familiar with are supervised learning applications where we use human experts to help use data to train the algorithms so that the algorithms can be as smart as possible, and then they can then automate the expertise that humans have been using to evaluate and tag the data. There's quite a bit of new data for which we don't have enough human knowledge about the data, and in those situations we'll use unsupervised learning techniques to help us group and cluster and evaluate and identify new patterns in the data, and then use that to inform our human experts as well as our supervised learning algorithm techniques. So it's an interactive process, but and it's again, I think the poll reaction about there being, the majority of people think it's complicated. It is a bit complicated because there's a lot of moving parts, but we also need to understand which pieces need to interact with other pieces. And that's one of the things that we're all learning as an industry. Just a quick listing of some of the more popular statistical tools. As I said, in machine learning, the core algorithms are built on statistical techniques, and it's important to understand what the initial conditions need to be and what the limitations are for each statistical technique. We've all heard about neural networks recently, I'm sure, with some of the results from being applied to different kinds of games. Neural networks are a great way to use parallel processing to perform some of these statistical analyses and help speed up the processing of the high volume data. So the next question is, how do we maximize value from all this coastal sensor data that we're collecting, and how can AI help us there? Well, we already have a lot of data. It can be layered in a lot of different ways. This is an example of the USGS Geographic Information System layers. But what's happening is we're generating a lot of new data from a lot of new sensors. For example, our sea ecosystem has a lot of new sensors that are collecting data from below the surface as well as above the surface. And the thing one of the challenges here is that the water column is very important. This is a four-dimensional process that we really need to understand better. In addition to that, we're getting a lot of new data from the watershed ecosystem, the waters that flow off the land into the sea. And that data is also coming from below surface and above surface and generating a lot of new information. So the big question is how do we fuse all this data so that we get information out of it? Well, fusing the data means we have to collect it, we have to prepare it, we have to analyze individual data streams. At some point, we hope that our machine learning algorithms can help us extract new features, identify and sort the data automatically and learn from it, and then inform our dynamic models and our forecasting models in such a way that they get better and better. And of course, this is an interactive process that we learn from. As everything we learn at the high level, we can help inform what we need to be doing at the lower levels of data analysis. So some of the current examples of AI applications for coastal waters include, and you'll hear more about this from the next speakers, fishery management, harmful algal bloom analysis, and aquaculture process improvement. Let me talk a minute for that. At Mote, we're building a Mote learning engine, which is a collection of machine learning algorithms to apply for aquaculture, which is fish farming. And we've learned it in research at Mote from our own aquaculture research park there, that we can improve the productivity of a fish farm by 20, 30, 40% by just fine-tuning the protein sources in the feeds. As we start looking at how do we fine-tune operational parameters on the each stage of the fish farming activity itself, as well as the feeds and so forth, we have great expectations that this will be a very useful tool for that industry. And we're beginning to learn how to apply this learning engine to other applications at Mote. So in summary, let's talk about some of the potential rewards we're hoping to see from using AI for coastal waters. More automation of data analysis so that we can handle more data more cost effectively. More discoveries from models and forecasts. In other words, we want to make our models and forecasts better, and hopefully our learning and the processing of the data from AI algorithms will help make those better. And then ultimately more value for societies, the science, and the economy. What are some of the risks for using AI? Achieving these benefits. Well, we're going to need more people with some new skills. We don't necessarily need more PhDs in statistics, but we're going to need more people that are able to deal with data visualization and understanding the conditions of the data that gets processed and how meaningful the outcomes are. We also have to make sure that our analysis capacity can keep up with the data growth. And then finally, is something that's cropped up in the discussions that I've been in over the last couple of weeks, has been that our data collection is still sparse. We are still trying to understand how much data do we need, when do we need it, and what kind of coverage do we need to have. Are we collecting the right data, and how do we get more of it? Finally, what are the potential challenges to using AI for coastal waters? Number one, we got to make sure our benefits cost ratio continues to improve. The cost of using these algorithms and data sources has to be getting better and better. Secondly, we want to make sure we have maximum value and that we can integrate our data analysis with existing systems and future systems to make them very valuable. And ultimately, as we collect more and more data from environmental and public health related data sets, we're going to come into questions about compliance with emerging rules on the use of data around the world. So anyway, I hope this is you find this helpful as an introduction, and thank you very much. Look forward to your questions. Sharon?
Thank you, Alex. We appreciate that. Next, we'd like to invite Rick Stump. Rick, could you share your presentation once Alex
there we go.
stops sharing his? Thanks.
Okay.
Great.
So I'll talk about, I guess, a particular problem on Carenia brevis red tide in the Gulf of Mexico. And just as a context on the cover, this is a severe red tide, and you can see it's not red, but the water is quite discolored. And this was in Pinellas County, bloom 2 years ago. Anyone in Florida would know that pretty well. For why does this matter besides the discoloration? A big part of the problem here is the respiratory impact, and examples, anyone who has asthma or potential other upper airway can end out in an emergency room. But people who are normally healthy experience severe respiratory irritation, watery eyes, runny nose, sneezing, coughing. For me, I feel like I've just suddenly come down with a cold as soon as I go on the beach. And of course, people want to avoid the beach, which has a big impact on tourism. Local businesses, restaurants are on the beach, and all the like. So those are the major concerns to address. ER emissions go way up in this, and the economic impact runs in millions of dollars per month in counties, individual counties. We've been working on a respiratory forecast with the what's called the Gulf Coast Ocean Observing System, part of the integrated ocean observing system that NOAA set up. And example, we take cell count data. This is from Pinellas County. Combine it with the most current forecasts and models for wind. And I should say, Carenia, the toxin can get into the air and end out as an aerosol that you inhale. That's how you end up with respiratory irritation. This is unusual for red tides. Most are other impacts. So we combine that, and we have been producing a respiratory forecast. Example here, and the nowcast is on the map, and you can see very low is the blue, high is the red, and it's very wide variation. There's some areas that are low in this region and some that are high. Whoops, back up. And then we have over time, it varies over time. Well, the spatial patterns are a huge problem. People live in Florida think if there's red tide, it's everywhere all the time, and that the respiratory is everywhere all the time, and that's not the case at all. There's a lot of variability. So it's very important to get the spatial patterns and temporal patterns as the blooms move around. So how do we get more samples? Well, a big question, could we use satellites, because they provide a lot of spatial distribution to get this? Additionally, could they inform other deployments? An SUAS, that's a small unmanned autonomous sensors, so drones of a sort, but ones you could deploy off the beach. And then could we even just use this to extend field samples? We still need analysis, but the idea is the more we can get about the concentration, the better off we are. And so for the big picture and where it is, there have been some new satellites in the last couple of years. Particularly European Space Agency has launched the Sentinel-3 series. and it has the Olchi Ocean Land Color Instrument, which is much more sensitive in our eye. There's a 300 meter pixel, which is about 10 times better resolution than the satellites that were available before this. And we get about 5 usable scenes per week with the 2 satellites, which is pretty good coverage. Of course, that does depend on clouds, which is a consideration. But I'll touch on that because in big picture is quite important. First, the satellite uses several bands of wavelengths that we can't see. So an example, true color on the left. And this is processed looking very specifically at a set of some red bands. So you can easily see the bloom with the satellite once we do the processing, where it's not possible to see it on a true color image. And there's a lot of information coming off a satellite. This is a spectra. 400 nanometers to 500 is blue, 5 to 6 is green, 6 to 700 in red, and 700 beyond is near infrared. And chlorophyll absorbs a lot of blue light, and then you have a peak, and then we have other pigments that absorb in these other areas. This is just a typical example, but many of the blooms look very similar. But it does allow us to identify the blooms. The little dotted lines are actually the satellite bands that are available. And one of the key ways we're approaching this is using chlorophyll fluorescence. Chlorophyll A fluoresces very strongly in the far red, about 680 nanometers. And so by looking at, this is actual satellite spectra, looking at this little peak here, we're able to pull out the actual bloom from the very densest to the less dense. So the height of that peak makes a difference. And you can see how much variation there is in that whole region overall. I should say, there's a classic George E.P. box that said, well, all models are wrong, some are useful. And that's an important, all good models, they're all going to be wrong to some degree, but they're useful. And so I want to point out that fluorescence and any number of other algorithms are not specific to Carenia. Example here, we have a strong Carenia bloom off the Panhandle. This is in September 2018. These are diatom blooms. They're also fluorescing in other areas. So that indicates there's more information that is needed to work with this. Just to capture the value of it, here's an example of the development of the bloom in 2018. Again, this is the very severe bloom. And you can see in July, the satellite indicates it was south of Venice, very tightly focused, and then it expanded to cover the whole coast. This is almost 200 miles from Clearwater to Naples. And if I flick to the state cell counts, which are weekly data on shore, you can see the same information. And that week in July, this is southern Sarasota, northern Charlotte County, whoops. And then it expanded over the whole coast. And if I flick back and forth, you can see how the satellite is actually capturing that information, but like a lot of patchiness that you don't see. When it was at its most intense in September, there are some areas near Venice where it was offshore, but not at the beach and near the coast in this area, and very intense area up towards Sarasota. So a lot of variability overall. And that's very important information to consider, which you don't capture just by the weekly cell counts, as impressive as this is. So we take the respiratory forecast to Pinellas, we put this together. So big question is, this is 1 day's worth of data. Someone has to go out, collect the water sample, bring it back, then it has to be analyzed in a microscope. This is a lot of work. It's extraordinary that they were able to do this for a while they were doing it every day of the week, but they were doing 4 to 5 days a week in Pinellas during this bloom. So a key question is, can we get to the shoreline? Well, the satellite shows some promise, and this is our Sentinel-3 on the left with our detection, and as an example, there's another satellite, Sentinel-2, but it only goes over every 5 days. But you can see an area, this area A, where the Sentinel-3 is not showing any signal right at the coast, it's all black. But with this enhancement, we can see this red indicates red tide. We enhanced it specifically with that color. And you can see it's actually right at the beach in that area. In contrast, the patches offshore are being picked up very well. So we do have a question, are we ability to resolve when we get close into the beach with 300 meter data? And 20-meter data, though, is every 5 days of the week. So we start getting to a challenge in trying to merge these data sets together. And that gets to some key questions. One goal, we are right now working on developing a small UAS for real-time monitoring near the beach. The idea is it can be deployed right off the beach and immediately return data, the same type of data we'd be getting from the satellite. So we could actually monitor that very close-in bloom as it flies over. And it would literally be doing this kind of zigzag. So the person at the beach would get that information. What that could do is potentially tell us bloom presence, might be able to feed that into the models. It certainly allows us to more carefully direct water sampling. We've also developed what we call the HabScope, which is put an iPod together with a microscope and doing using TensorFlow, which you'd heard from Alex. We can actually identify the Karinia and count the cells on a video and return that information. So we're working on trying to enhance from both sides the ability to monitor big picture, to transfer that into shoreside deployment, either from drones and actually to more target and speed up the sampling whole process. We are working with several of the counties and also with the state of Florida and trying to incorporate that capability. And then now that would feed into our respiratory forecasts, which the idea is to get to what we'd say, trying to get to every beach every day as a goal. Now there are overall challenges in remote sensing. The community works very hard on, there's a lot of people who do optics and bio-optics. And so the goal is looking at pixels and looking at the bio-optics of the spectra of the pixel. And I call that the Holy Grail. And because that's what everyone would like. And as you know, your King Arthur legend, it's not achievable. No one's going to find the Holy Grail. And the practical part is the Karinia brevis is a dinoflagellate. It looks like other dinoflagellates, and they look very similar to diatoms. There's also interference from other things in the water, from the bottom. The water is relatively shallow. Sometimes the wind stirs up sediment. And so a lot of interference will mean that we're not getting the information we need. So we can push this as far as we can, but we need more. And as I noted earlier, fluorescence is not specific, but if we know more information, we can pull in other data. One strategy is to bring in ecologically based modeling. Example, we have been working on what we call new blooms in the fall. So we look at anomalies in the chlorophyll A. Did anything new show up? And fall blooms on the Florida shelf are typically Karinia brevis. So we already have a very simple ecological model that if it's a bloom in the fall, we're probably seeing a Karinia bloom. Blooms other time of the year probably are not. There's also other ecology, salinity. Karinia does not like low salinity water, so a bloom, for example, in Tampa Bay might be pyrodinium, which is hazardous in other ways, but it's not, does not cause the aerosols. There are other aspects to look at besides that. Biologically based models. Karinia brevis and other dinoflagellates swim, whereas diatoms, which are the good algae, they don't. And so we may see variations through the day because Karinia brevis is phototactic. It swims to light, so it tends to disperse through the water overnight and swim to the surface during the day. It may change with other factors as well. So potentially getting more data or looking between times. And then another component on this is relationships. And when we look at optical based, we're thinking pixels, but we're not thinking about patches, which is spatial relationships. A bloom is a patch of, will be in a patch of water, is not a pixel. And so looking at relationships between areas, we can find blooms as patches. And the characteristics of those patches may also tell us things. Blooms also last for weeks. And so an assumption that we have to look at a pixel by itself independently without considering its context in time or space is really not a good approach. Each image, as I said, is not a blank slate. We have pre-existing information. We may have identified the bloom from water samples. We know what was happening the last image or the last week. So all that information can be pulled in. And as you look through this list, you can quickly see needs for what would be AI strategies, because we're quickly getting to a lot more questions and capabilities than one person can do with some simple analytical rules. And it becomes important to try to capture those together, and how do we merge those together, which becomes a key job for trying to do an AI approach. In the overall, in order to pull this off, we really need ready access to data, new types of data, and also model output. And this is a whole range of models, from whether it's hydrodynamic or weather models for wind conditions and that sort of thing. And then other data sets. My experiences with data is, if I'm trying to work with something, I seem to spend 95% of the time just trying to get the data in a form I can do something with it. And those aren't fairly easy data sets. We get into the big data question, and I think capturing Alex Beaver's point of, we need data scientists so that I don't have to figure out how to be a data scientist. I can work on the methods and the approaches rather than doing that work. We definitely need new technologies for evaluating the remote sensing data to include all these components. And then we need this to actually inform the other methods and applications that come forward. Is how do we get the right information out to the public? How do we make sure we're integrating this so it's easy for a county to go sample or plan their strategies for the week? And all of those pieces would come together in this approach. So wrap up there. Thank you.
Thanks, Rick. We appreciate that. Farron, would you go ahead and upload your presentation now as well? Thank you.
Okay. Okay, I'm assuming that's showing on your end.
Everything looks good. Thanks.
All right. Hello, everyone. My research and my presentation today is going to be focused on developing AI for monitoring fisheries. All of this work has been done in collaboration with a lot of folks out there, including the fishing industry, Alaska Fisheries Science Center, and the University of Washington. Okay. I'm having trouble advancing down here. Okay, there we go. And so NOAA Fisheries, they recognize the importance of developing AI. And so we have a new draft AI strategy that we're hoping will dramatically expand the application of artificial intelligence in every NOAA mission area by improving the efficiency, effectiveness, and coordination of AI development. Particularly important for developing AI and machine learning for fisheries is AI methods such as machine learning to provide the transformative advances in the quality and timeliness of the data. And so what is machine learning? Well, it's computational learning using algorithms to identify patterns and form and make predictions on the data. So machine learning is a part of AI, a type of AI. We see the impact of machine learning on EM is going to be really important and will play a fundamental role because it provides a really credible, cost-effective avenue to collect and analyze enormous amounts of data at the source or at the edge. And so this is especially important for electronic monitoring because it's going to cut our costs probably in half, because it costs a lot of money to go down to the boat, collect the data, pull the hard drives, bring them back and upload them to the server and do the annotations, and then apply the analysis, machine learning analysis. So it is a big challenge, but I think we've made a lot of advances over the last few years. But this challenge is absolutely necessary to make electronic monitoring become much cheaper and start using it much more broadly across a lot of different fisheries. Our objectives for remote monitoring, one is to develop remote monitoring systems that support the latest developments in AI to improve system functionality, reliability, and timeliness of data. The overall thing we want to do is provide an end-to-end solution, providing a fully automated system. And so we see this system that can see, learn, process, and transmit the data all automatically. So we don't have to go down to the boat and pull those hard drives off. We don't have to have a technician sitting in the office processing the data and uploading it to servers. So first I want to start with a couple of really big considerations if you're thinking about developing a new innovative system for monitoring fisheries. The first of this is a system design where both deployment and implementation choices are highly critical. The time to develop automation and cost will be directly related to the design of your system and how complicated or uncomplicated it really is. And of course, with fisheries, it's very important that you have vessel monitoring plans. You have to have the industry on board to work with you, and so they know what their requirements are going to be to ensure you're not collecting biased data and you're collecting good value data and imagery or sensor data of high quality. Of course, along with all other AI, machine learning, the most important part is those training data sets. And so you have to have training data sets that cover the scale of the data to reasonably capture all the complexity in the problem. So if you're out collecting data on a fishery, a longline fishery in the open environment, that type of situation, of course, is going to require a lot of data collection and a lot of much more analysis to cover all of those wide-ranging changes in the environment, changes between the vessels, changes in the species composition. So the bottom line is that this means there needs to be enough data to reasonably capture the relationships that may exist between the input data features and the output data features. So now I'm going to show you 4 different examples of increasing complexity of some of the work that we have done. The first example here is sort of an easy one to develop automation for. This is a camera shoot system that has been deployed to a factory trawler in the North Pacific. And they have to take the halibut when they come on board, and they have to throw them back over as quickly as possible so they don't die. So it's really important that they get these back over, and so samplers just don't have the time even to sample them before they go back to sea, but we still need the data. So let me start this video here. And so in this system here, the system automatically identifies whenever a fish is slid through the chute. It identifies that species, and it also takes highly accurate length measurements. Again, here's a system that has consistent camera angle, consistent lighting, and this is what makes it really much easier to develop automation for. And this is the first innovative tool that we put out and started developing AI for. Here's an example, sort of medium difficulty. This is in a processing plant in Kodiak, Alaska. So these guys are supposed to pull all the salmon, and you'll see the red boxes that are finding the salmon in the catch. They pull those salmon and put them into a tote so we can weigh them, and we have to have full accountability of all the salmon. And so this is a compliance issue, and so we want to make sure that the factory workers are pulling the salmon. You see them pulling the salmon here from the belt. This was just a pretty small training set data. You can see it's a little less than 6,000 images or annotations. And just with this small data set, we were able to get a recall rate about 70% identifying salmon. Now, obviously, this would be much higher if you want to know the species of salmon, or if you want to look at multiple fisheries that are being processed in the plant. And that, as the complexity gets more and more, it's going to take much more time and effort and cost to develop the machine learning algorithms you need to do what you want to do. All right. This next one here, again, this is sort of another medium level complexity. And essentially what we're doing here is trying to determine when a catch event, so when a fish is caught or something is caught on the line. Little explanation here, the green colors represent the sea, the red color represents the ship, and the little white line you see down below is essentially a cross angle of the ship in the sea. This was sort of a major advancement that we made, because you want to know But when a catch event happens, but you have to discern it between the sea and the ship, and if you have dark fish coming up along out of dark water, it's really difficult to do that kind of things because they just don't stand out very well. So let me play you this video, and you should be able to watch the lower panel, and you'll see when a fish is being caught. There the fish is coming up. And so this development, we're able to get about 99% of the catch events being caught. Play it one more time. And you can imagine there's other complexities that come into here, especially in the environment and in the North Pacific. It's dark, the lights are shining and everything else. So again, this one piece has helped us tremendously in identifying those fishes. Okay, next one here is a very difficult example. This is a hook and line vessel, again, working up in the Bering Sea, catching halibut. And for the halibut, we need some really important information such as length, and so we know what the total catch is, and we want to know what the bycatch species are. The yellow box here represents a bounding box, which is a 3D box that the analysis draws around each of the catch. These are with stereo cameras, and so we have fairly good depth for each pixel on this frame here. So let me play this one here. And you can see how complex it really is because the fish can be facing towards you, flopping towards you, or flopping away. If it's flopping away, you may not see the head or the tail. And so it's very difficult to get an accurate measurement if the fish is facing away from you or bent away from you because you can't see what you can't see. The other part of this, of course, is species identification. That seems to actually be a little more simple than it has been to get accurate length estimations every time. But again, it poses a huge problem because one fish comes up and you probably get 30 or 40 frames of a single fish each time. And it is in every different type of pose you can imagine. And so you have to have an algorithm that takes into account all the differences between each of the poses. And for this fish here, it has taken many annotations. I'll talk about that a little bit more to try to develop. Okay, so the question I think I get more than anything else is how much data do you need for training new algorithms for machine learning? The yellow line here, that probably represents the chute system that I showed you. You probably need, tens of thousands of annotations. It'll depend on how many species. In the North Pacific, I think we're estimating around 80 different species at this point with fairly high accuracy. And what it really comes down to, though, is how many species, especially those rare ones, do you have to accurately identify? And the higher that number is and the lower number of samples that you have, much longer it'll take. This curve here, this is sort of the medium complex situation, such as those in the Bering Sea processing plants. And here we need hundreds of thousands of images to properly identify salmon within a pile of catch. Again, though, it's not foolproof because you can't see whatever's going to be laying underneath the fish. And so we can have different compliance rules that would make them essentially spread out the fish on the belt so we could do this. The third one here's that complex situation from the multi-species fisheries, the hook and line fisheries. This is very difficult to do, not only in terms of species identification, but also for deriving accurate length measurements. Here, I think we have well over 1 million annotations developed for this fisheries. And so in terms of species composition for estimating species, we're pretty good on that for all of the major species. Again, we're still striving to write various algorithms for determining which fishes or which pose of those fishes that we need to focus in on to get accurate length measurements. Okay, next consideration is another really big one, and this is after you have developed an algorithm that you think is doing really well. It's really important that you validate that your estimator, your algorithm is being consistent. And so you have to use sources of information of human versus machine, and make sure it's identifying and counting and measuring correctly. And you shouldn't just do this once or twice and go, well, things are working well. It is super important to get out there and do it even after you've been in this process for a while. The second part of this, I think most people don't realize, is that you need to maintain your algorithm. You want to make sure that this algorithm is properly tuned to guard against drift. You can imagine that in a fishery, you're catching all these different species, maybe via a different vessel, in different environmental conditions, catching a few other species, and your algorithm just is not going to do very well. And here we developed a couple of tools to ensure that we have a good algorithm, or the algorithm being maintained. One of them is query learning, and here we have automated feedback where the system will mark those images that go, hey, I don't know what this particular fish is, and then a human or observer will come in and identify that fish, and then they'll feed that back into the training data set. So that once you do this for a number of fish, then you have to update all of the electronic monitoring systems you have out in the field. There's a number of key milestones that we see for Southeast Fisheries Science Center. I'm not going to go into any detail here, but essentially in between 2020 and 2021, we really want to build trust and partnerships with the industry and all of the NGOs out there. We're going to be deploying those systems as much as we can and building the image library. In 2022, the National Image Library should be coming on board, being built by NOAA Fisheries. And I think this is really going to help us store and analyze all of the imagery that we've collected over time and develop even better AI for monitoring fisheries. In 2023, at the same time, we're going to be developing high capacity systems, because again, as I mentioned, we have to be able to process the data in real time on the vessel to make these systems cost effective. In 2024, we hope to get many of these next generation systems developed and out into the fishery on a much wider basis, so we can again start refining our innovations. Lastly, I want to leave you with this last little video clip here. This is a hook counting, and I just think it shows a good example that if you have good data, and in this case it's imagery, nice bright imagery, is that you can write algorithms to even identify the smallest of things, and here we're identifying and counting hooks. And with that, I'll certainly entertain any questions now or during the other sessions.
Great, thank you so much, Farron. That was really interesting. I am going to take a question or two, and then we're going to just jump right into breakout groups, and then we'll come back at the end and have a few more questions for because we got a lot in the chat box. Rick, a question for you from Jennifer Dorton. There's a lot of red tide work on the west coast of Florida by state agencies, NOAA, university researchers, etc. How coordinated are these efforts, and is there a centralized place to find out who's doing what?
Well, the work is well coordinated. We work very closely with the state. Let's say everyone works closely with FWRI or FWC, the Florida Fish and Wildlife Commission, because they're the lead agency in Florida for collecting the data, and that provides key linkage. As far as coordination, the different groups on their websites try to at least cross-link to each other. Data, that's more work needs to be done, and trying to work out how to best coordinate that.
Okay, great. So that's going to be one of the questions that people will be talking about in the breakout session. So just before we head to breakout, Farron, I had a question for you from Christine. How might you detect whether drift is actually going on? And secondly, what other types of national image libraries are now needed to support such automation in other sectors? That's a two-part question. Do you need me to repeat the first part or?
Sure. Yeah, well, for the first one, you have to, again, this is where validation comes in. And so as you're collecting the information, you always want to continue your validation. Then that's what's going to tell you whether or not you're getting drift in your algorithm over time. The other part of that, though, too, is that every time you estimate what a fish species is that it'll actually also develop an uncertainty value for that. And so you don't necessarily have to accept a fish that the estimation was only like 30% certain, for example, something like that. And the second part was?
What other types of national image libraries are now needed to support such automation in other sectors?
Well, that's a good question. I've been pretty much focused in on electronic monitoring. And we're at that stage right now where every region is sort of developing their own image databases. The national image data set should be coming online over the next year or two. And the idea is that we'll all upload our data, our imagery or sensor data into one central repository. And then this way, then we can have a single source that contractors or other folks can come in and develop AI.
Great, thank you, Farron. So we're going to head right into breakout groups now. We'll have 4 questions today and we'll have 8 groups. So groups 1 to 4 will be focused on questions 1 and 2, and groups 5 to 8 will be focused on questions 3 and 4. If you get through those and you have time, go ahead, please, and answer all of the questions. And so I'm just going to send everybody off now and we'll pull you back here in about 20 minutes or so. Thank you so much and enjoy the conversation. Starting to look like everybody's coming back. I'll just wait for another few seconds to make sure. Well, I tried to give you a few extra moments in there just to make up for some of the time. So how about we start with the first couple of groups? Would somebody from groups 1 or 2 or 3 like to say or share a little bit about what you discussed and some of your main insights?
This is Alan. Yeah, I'm going to turn it over to Peyton. She's got all the notes and she did a great job for us, by the way. So Peyton, can you take that?
Yeah, sure. Happy to. So our first question was, how is AI currently being applied for marine sciences in coastal waters? And we discussed a little bit about fisheries and stock annotations for fisheries and how AI is currently being used to help identify species in particular. So being able to take these large databases that are currently being filtered through manually to identify species and high migratory species in particular, and identify all those pretty quickly with AI as opposed to just going through photos on a more hands-on basis. So there was that, and then we also discussed waves and identifying those with AI technologies and how AI is being utilized to take certain wave conditions and compare them to weather situations and match those up so that it's a lot quicker to see, based on weather conditions, what kind of wave environments we can expect out of that. So that was the majority of our first question. And then our second question was, what capabilities are required to improve the conversation of coastal sensing data? And a lot of what we focused on was more social science and discussing how we can get the information that's being gathered in these databases out to the parties who need it. Because so much of what we focus on is how to actually get this data and gather it in a meaningful way. But if it's not getting to the folks who need it, then there's more work to be done there. So for instance, with hotel owners, you might need different information than if you're a fisher or if you're someone who's looking to plan a vacation soon, particularly around red tide, focused on that a lot. So that sort of encompasses our group. I'll hand it over to the next one.
Thanks, Peyton.
Thank you, Peyton. Appreciate that. Would anyone from groups 5 to 8 like to comment and share right now? I can pick you. How about, let's see, who's the note taker from group 5? Bernadette, would you like to share for your group?
I'm going to defer to David. He's the note taker today.
We
Oh,
switched,
David's gonna
we
take it.
switched
Okay.
roles because, just to spice it up a little bit. So,
Switching it up on
uh,
me. Okay.
all right, so we were answering to how to identify and increase access to available data sets and create useful products. So there were kind of two main sort of categories of answer here. And the one Ryan shared with us was that the idea that it really, the types of data that we're trying to get consistent and usable, like training data for, are a function of the end users. So the idea that we can build similar regional training data sets, and there are a lot of data out there, but bringing them together, and the idea of kind of throwing it all in the same bucket, allowing these useful sort of data fusion products to work, but bringing together, what may be sometimes proprietary data or people's own data that is collected towards a specific goal, but that could be expanded in utility if it was shared with others. We got a little bit into the question of data sharing concerns in that mode. So if we have an end user group and you give all your data to throw into that bucket, how do I know that my data is being properly shared and QA/QC'd? A lot of people will put out their data with their own kind of caveats about it. And once you start sharing it, they're sort of hard to maintain. And that led us down the road of saying, there's a role for funding agencies in this regard. So maintaining or requiring that data sources and methods are publicly available would be, it's already done. We had an example of NASA data requiring it to be shared on their portal in a certain way. But that if that is a mode for getting more data out to more people is through the funding agencies. And then Mayosion added that if you start to put together some of these data streams in the same bucket, that's when we start answering questions that cross sectors. So you might be interested in fish, and Rick Stumpf might be interested in HABs, but then you might start answering questions about how HABs affect fish. And so that's a really sort of powerful, it's not a new source of data, but it's a new insight from combined data. So I think that's what I'll say for question 3. And then for question 4, about current and future workforce training needs, it might not be a surprise that we talk a lot about communication, and we sort of identified the idea that there were AI producers. So these would be more the computer science, data science folks, and then AI users. So these would be the people that have a specific objective or question they're trying to answer. So we talked a lot about interdisciplinarity, that you can't do it with just computer science, can't do it just with biology, but we need to have workforces that are sort of broadly trained and particularly trained, not necessarily in the guts of each discipline, but in communication and in critical thinking, and sort of acknowledging that the AI solution is only part of the solution, but the critical thinking skills are going to be required, even if we put it all in the same bucket. And then another point was that it's not just communicating between the producer of the AI, GWiz tool and the user, like for example, trying to get the fish count, but then the user for the fish count data has to communicate to the public. These data, these insights came from an AI-based algorithm. So what does that mean? Like, what does accuracy mean? What is, what are the caveats again that are left on the table by using this approach? So that's where we got on those 2 questions.
Great. Thank you so much for sharing. I'm mindful of the time, so I'll just let you know that we will keep the chat open, and we'll also stay on with some of the speakers if people would like to stay on and continue the conversation after we do sort of the formal wrap up. So we can ask more groups to share at that time, and then we can also get some more questions answered by our speakers today. So with that, I just want to thank you all for coming out again today, and hope that you've enjoyed the experience once again and benefited from the rich conversation. As I said, we're going to leave the chat open. We've also posted our survey link, so if you can copy and complete that survey, we'd really appreciate it. That'll be super helpful. And I'd like to invite Christine now just to say a few words in closing and to kind of give us some forward-looking view of what's going to be happening at our next session, which is in 2 weeks' time. Christine?
Sure. So I want to thank the speakers for giving some really excellent talks at the beginning of the session. Thank you very much to Sharon for doing such a good job at emceeing all of this all the way through, and Amanda also for supporting her, and the summit organizing team for putting so much time and effort into getting this sort of conceptualized and then brought to fruition. So next steps, we're sort of in the fourth of the 5 webinars. So what's ahead? In a couple of weeks, on July 15th at 1 p.m., we will have our final session of this Innovating Coastal Resilience Summit. And in this final session, the goal is to try to pull together all the feedback that we've gotten over all of the preceding sessions and have some highlights and synthesis about where we see research and workforce training needs being moving forward. So that'll be presented in sort of a summary synthesis that spans all of the preceding webinars. And we will hope to get your final feedback on the accuracy of us being able to capture your input, but also to talk about what we each can do sort of moving forward, both individually and collectively, to move the needle in these areas where we see sort of innovation being most exciting moving forward. So the last thing I want to say is that another mechanism of sort of engaging is that we are genuinely interested in building partnerships with all of the entities that we invited to participate. So, we hand selected our audience, and because they're people that you have expertise and experience that we would think would be really valuable for building collaborations with. And so we encourage everyone to reach out. You can get in touch with myself. My sort of contact information is in the chat right now. On behalf of Mote Marine Lab, feel free to reach out to Alex Beavers or Tracy Fanara. From the Innovation Station at the University of Florida, please reach out to Patricia Harris, if you're interested in sort of local industry innovative sort of ideas, especially in Sarasota County, as well as Natalie Nelson from North Carolina State University and Bernadette Kelly from FAMU. So we have had a lot of time and effort from these folks, but the goal is for us to all start lighting up our connections across this network and better using our partnerships to really move the needle moving forward. So we encourage you to do that amongst yourselves, but also with the team, that organized this session. So hope to see you in a few weeks. You get a reprieve of emails from me for a few weeks. And thanks so much for your time and attention, and look forward to any final comments you may have in the final minutes here.
Thank you. That's a great note to end on. Thank you, Christine and Amanda, and our speakers, Alex, Rick, and Farron, and to all of you for participating. And we hope to see you again, as Christine said, at our next conversation on Wednesday, July 15th from 1 to 2:30 p.m. Have a great afternoon.